Hello, everyone, and welcome to another virtual meetup. We're so excited to have you today. So we'll get started here shortly. We have George ready to go and present on the machine learning tree. But first, we'll go through our typical agenda. So real quick, introductions from the Elastic side. My name is Olivia Petrie. I'm a program manager, and I'm also joined by Justin.
Hey, everybody. Justin Castillo here, a senior developer advocate at Elastic.
Perfect. So I'll run through a few of our upcoming events. We have our typical meetup raffle, cover some of our resources that you can take advantage of, how to get involved in our meetups if you're interested, and then we'll turn it over to George. At the end, we'll have Q&A. So if you have any questions, please post those in the chat, and we'll get those answered at the end with George, or if it's something that Justin and I can answer, we'll answer them directly in the Q&A in the chat box. So with that, upcoming meetups, these are just in US, LATAM, and Canada. We, of course, have Meetups Global. So I will post a resource for you to check out any upcoming events in your neighborhood. These are what are scheduled about a month or so out. We're constantly scheduling new events. So definitely find a user group that's closest to you and subscribe so you can stay up to date. Again, we have our typical meetup raffle. We will be raffling off some Elastic swag. I will post this link in the chat as well, just because I'm sure it's not, I can't sit on this slide long enough for you to type out that URL directly. But if you are interested in winning some swag, feel free to enter that. Of course, we have our Elastic resources from our DevRel team, community YouTube. That's what this video will be on after we're done with the live stream today. Really great resource for, meetup recordings, beginner series, solution-focused videos. We have our Discuss, which is our forum where you can ask questions, answer questions, get help from the community and other Elasticians as well. And then, of course, our Elastic Slack community workspace. I will post all the links to these resources again in the chat here shortly. What now? So if you're interested in presenting, whether that is at a in-person meetup or a virtual meetup like this one, definitely reach out. We want to hear from you. We want to hear your Elastic use case. So send us an email at meetups@elastic.co. And then, of course, find the nearest Elastic user group chapter and subscribe to stay up to date with upcoming events. So with that, I will turn it over to George.
Let me get my thing going. Hello, everybody. So let me just see that. There we go. That looking okay to everybody?
Yeah,
that looks great.
All righty. So thanks so much for sacrificing your lunch hour to this presentation. Let me jump into it. I'm from SEMplicity. I've been working with Elastic for the last 8 or so years. I've given a few of these in the past over the years, thanks to Olivia, and thank you very much, Olivia and Justin, for helping me out with this. This is just my abstract, but I think the only important part here is the audience, right? Usually my presentations are cookbook sorts of things where I should, take people through exactly how we're going to implement this, that, or the other thing in Elastic. There's always new stuff coming up, so there's always new cookbooks to do. This one's really different. This one's more of kind of my journey towards understanding machine learning here in Elastic. And it's a high-level presentation in some sense. It does get down into some statistics, but generally it's kind of less to tell you how to do something and more to tell you how to make sense of all the different features that are in Elastic. So my audience is kind of Elastic stakeholders who need to design use cases and understand the different things that machine learning can do and how to make sense of it all from a standard framework. It's especially geared towards security and observability practitioners, because that's where we spend most of our time, though we do a lot of work in search these days as well. And it's for data scientists new to Elastic. So those are our that's our audience here. I think that if you were looking for like a deep dive into how to write specific machine learning use cases, this probably isn't for you. But if you want to try and understand all of the elastic machine learning components and how they fit together, or almost all of them, then this is for you. So I thought I'd push that here at the beginning of the meeting, so that people, if it's not for you, you can leave. So without further ado, let's jump into this. So we'll start with like I think a lot of people. I've been following machine learning since around 2008 or so. Really, a little bit before that. We first started doing anomaly detection back in 2006. Obviously, not with Elastic, but I've been following it a little bit because I was interested in the statistics behind it, but I wasn't really doing too much with it until about 3 years ago or so, when it really sort of Elastic. I really started to see the applications for it in the Elastic stack. All we do around here, all I've been doing the last 6 years or so is Elastic. So when I started to bounce into it, I was just really bewildered by this blizzard of buzzwords. That's a pretty fun way to put it. And like how they all fit together. Like there's just so many buzzwords with this stuff, with security analytics and data frame analytics and time series analysis and, anomaly detection, supervised learning, hyperparameter. I just created a, word cloud here. I could have been much more confusing than that. And how this stuff fits together and how it fits together with the rest of Elastic too, in terms of transforms and things like that. So I was really kind of banging my head against the wall with all this terminology and all these different buzzwords and what they actually mean. And then, I had sort of a breakthrough, and here we're going off the reservation a little bit here. I had a little breakthrough because I got back to sort of what I was doing back in college. I graduated in '83. And back then, I needed to make money in college. And rather than like work in the dining hall, I got a job handling pigeons. And what I did with the pigeons was it was in the psych lab. And I would take the pigeons and I'd throw them into something called a Skinner box, because that's who was running the psych lab, B.F. Skinner. And we would train them to do things, and we would capture which way they pecked, one way or the other. It was all automated on computers, and it's actually how I got into computers. And we'd capture all the telemetry. And then what we would do, this is back in the 79 to 80, we would create regressions. We would try and fit lines to data. And I would help, eventually I went on to help write some of these regressions. This here on the left is I don't know if you can see my pointer. Let me just try and see if I can do that. Hold on. So this, let's just do a laser pointer here. So this on the left is a Skinner box. This is what we put the pigeons into. They were very well-fed animals. They lived 3 times longer than in the wild. And we would measure, we would do things to them like flashlights or show lights, or just feed them if they pecked a bar. And then we'd measure everything they did. And the head of that was a guy named Fred Skinner, who was a great guy. He wrote a lot of interesting books on behaviorism. He's sort of the father of it. And his favorite thing to say was, we study humans to understand the pigeon mind. At least that's what I remember him, but some people disagree. But the point is that it was all about fitting lines to data. You have a bunch of observations and you run a regression, and it fits the line to the data. And you do that to find correlations between variables and validate hypotheses. And then you create formulas to generalize behavior so that you can predict what's going to happen in the future. And once I managed to remember way back then, all of this stuff started to make sense to me, because that's all machine learning really is. You're going to model data and build a model of that data, a mathematical model, and then you're going to do things with it. You're either going to use it to evaluate new data coming in, or you're going to use it, to predict new data coming in, to detect anomalies, to classify data, to find correlations between data. It all comes down to these regressions that we were doing back then. Back then, I would say, in the early 80s, I'd run like a 2-variable line regression, and it would take overnight sometimes with the data we had. And then at the end of the day, I'd have sort of a formula which you would then tweak and run again. And that was now, we run, I actually think, millions of these things on some of these jobs. Just, we run millions of them on the Elastic Stack, and it runs in like 10 minutes. That's the big difference, but it's the same idea. And that's sort of the main point of what I'm trying to get across here is machine learning is all about line fitting. And if we understand that, then all these buzzwords are going to start to make sense. So here's my generalized model of how all this machine learning works in the Elastic world, or in really any world. Basically, machine learning takes two kinds of data, and the twain don't really meet. You use the different data for different things. So we take unclassified data, which is data where we don't really know, it's not labeled. And then we sometimes take classified data, and that's the difference between supervised and unsupervised machine learning. The unsupervised machine learning is we take in raw data and we try and model it. We try and, like with all this stuff, we try and model it and create formulas to predict it, and we run all kinds of regressions to create a model of what this data looks like, and we're looking for patterns. And then with that, we can detect anomalies, because once we've modeled it, we can see when something's out of the ordinary. When we take classified data, we also model it, and we try and determine if a new piece of data comes in, which class will it fit in? And that's what the learned machine learning, the supervised machine learning will do. So we take two kinds of data, but either way, we're always going to build a model, and that's what the machine learning job in Elastic does. It builds a model, and the model is actually nothing more in Elastic than an index, and that index contains the model. And as we'll see for the anomaly detection, it's always changing its model. It's always building new models. That's the way it works. It's always taking in new data and updating its model. For the supervised machine learning, it's building its model once in the job, and then we're going to use that model until we rebuild it. So that's the difference between them, and we'll talk about that a little bit later on. For anomaly detection, we're looking for we're continuously rebuilding the model. That's the difference there. And then once we've built the model, we're going to actually, it doesn't really do anything for us just sitting there. We have to take new data that shows up and feed it into the model. And then the model will tell us stuff about that data. And it will tell us only two kinds of things, really. It'll tell us if the data that's coming in is weird and anomalous, like it wasn't what the model was expecting. I expect to see 100 records at this time of day, and I saw 1,000. That's not great. So it's going to predict anomalies, and that's what Elastic calls anomaly detections. And what it comes out in the wash is we can do forecasts as well. Or it's going to make a prediction based on the model, based on the record coming in, as to what kind of record it is. We're going to try and classify that document, and that's what our supervised machine learning is. So what we've done is we've taken 1 million documents that have been classified, our classified data here. We've created a model to help us when a new document comes in, to classify it one way or the other based on what we've seen in the past. And that's what we call inference. And from that, we can get predictions about what we think this particular document is based on all the other documents we've classified. So that's a simplified version of the way it works. But this is a good way to remember it, because the different buzzwords are going to start to fall into place now. We can only, as we said, we can only generate anomaly. We create a model, it gets new data. Out of that model either comes anomalies or predictions. So with that said, let's see, we're just taking questions on the Slack, so we'll deal with that later, or on the chat. But let's take a breath here, and then let's look into, now that we understand how this stuff works on the base level, it's just line fitting. Let's take a dive into the different kinds of Elastic machine learning, which have aggregated onto, created on top of each other over the years here. So I'm going to start here on the right. So this is unsupervised machine learning. That's Elastic machine learning is divided into two trees, two branches, right? We've got supervised and unsupervised. Let me start on the left with unsupervised. On unsupervised machine learning, that's where the data is not labeled, and it's almost always time series data, which means that it's like transactions, logs, that sort of thing coming in. And we are looking at each of those things and we're building our model. And the way we handle time series data is we chunk it together into buckets and we capture the information for each bucket that we're trying to model. So the sorts of things we can model are record counts, which is the easiest thing to model. How many different records, how many different documents of this type came in. And from that, we can detect spikes and lulls. And that is the simplest unsupervised machine learning use case. Is this particular device, we'll talk about them in a second, but is this particular device not sending documents when it usually does at this time of day? Or is it sending way too many than it usually does? Then on the unsupervised side, the next simplest is the idea of a metric. So we don't have to model the document counts, we can model any numeric field on the document. So if we're getting stuff like packet counts in a document in a field, we can model those. And we can model statistically anything we want about them. We can say the max, the min, the standard deviation, median, distinct. There's all kinds of statistical functions we can apply against those numeric fields on the documents. And once again, what we're going to do is create a model, and then when we see some new data that violates the model, that's outside of the bounds, we're going to create an anomaly. But we can also do some really interesting thing with text, right? Because not all our data is numeric. So the unsupervised machine learning as well can categorize text, and it can create categories of text messages based on their similarity to each other. And so when we see a text message that really looks out of the ordinary, that we've never seen before, we can create a rare anomaly. We can say, hey, I got a message here that I've never seen. We can also model geographical locations. So we can say, hey, I'm getting data here from a geographical location, and it doesn't have to be like a lat longe, right? It can be an area like a country or a zip code or anything like that. I'm getting information from a place that I don't usually see stuff from. And it can also model time. So it's like I'm seeing activity like certain records like logons for particular users or such at times that I don't usually see them. So that's all how the unsupervised machine learning works. Now there's a special case of that called outlier detection that in my mind, because there's always one of these, right? It straddles the line between supervised and unsupervised. So all these blue boxes are for time series data. But sometimes we have stuff that's not time series data. We just have entities that exist outside of time, like a user. And we might have, say, like a user and their set of access permissions. And that doesn't exist in time. It's not bucketed. So for that, we have outlier detection, which also detects anomalies. So what it would say is a use case for that is like I have a user with a whole bunch of permissions, and I'm going to compare that to all the other users and all their permissions. And I'm going to go find the oddball, like, hey, this user's permissions don't look anything like anyone else's user's permissions. Maybe we need to talk about that. I don't talk a lot about outlier detection. It's because I didn't want to drone on here for a couple of hours, but I don't talk about it much in this presentation, but it's another form of anomaly detection for non-time series data. So let's bounce over to the other side of the tree. That's supervised machine learning. Once again, it's going to build models and it's going to do things with them. There's only really two kinds here. There's classification and regression. The classification is what I talked about when your data is labeled. And the regression is when, a label is a discrete thing. It's either like it's labeled as good or bad, or it might be labeled as 10 different things, 10 different types of customer. But sometimes data it has a dependent variable that is continuous. It's a number. So really, these are two forms of the same thing. For classification and for regression, what we do is we look at we take a dependent variable. If it's text, then it's classification. If it's a number, then we're going to do a regression. And then we take a number of independent variables, maybe all the all the variables on the document, all the other fields, or some of them anyway. And then we run a classification or a regression, and we create a formula to predict when a new record comes in. We can predict what that number, if we're doing a regression, what the dependent variable number will be. And if we're doing classification, we can predict the class. And for that, we use inference. And so that's the quick outline to how this stuff works. We're going to dive into all these things. Let's just start right in at it. So here I've bounced out these are the sorts of use cases, and for unsupervised machine learning, this is what we kind of use it for. So I talked about spikes and lulls, right? Is the device producing too many log records? I talked about the next step of that, which is just instead of looking at the record counts, we're looking at the fields on the record. If I have a field that says how many packets were dropped, I can sort of look for if the number of packets dropped is way outside of the bounds for that time of day. And then I can also do a statistical analysis on those, statistical transformation on those. Is the average way up? Is the median way up or way down? There are like a lot of distinct values for this field. So that's how we do metric fields, and then the categorization we talked about here for use cases. But I think that what you'll see, what I'd like to point out here is that and this is an important point if you're going to develop these things, there's two ways to model this behavior for unsupervised machine learning. We can model based on the device or a group of devices itself, right? We can say for this particular host name, model its behavior. And then for this particular host name, model its behavior. And then what we'll do is when we detect an anomaly, we'll find a anomaly compared to the past behavior of that device or that group of devices or that group of users or whatever. And that's what we call partitioning, or we can partition the data, or we can do what's called a population analysis, which is where we take we're saying we're modeling all the devices, all the users, and what we're looking for is an oddball device that is way out of line with all the other devices. So if you have, say, firewalls and they're all expected to have the same volume, and you're looking for a firewall that suddenly has a giant spike, then what you would do is a population analysis. It's much less resource intensive. So there are and all these anomalous, the unsupervised machine learning use cases can be run in one of two ways. They can be partitioned, say, by group or by user or by device or something like that, or they can run a population analysis against all the users or all the types of users. So that's the main thing to understand there. So when you create an unsupervised machine learning job, you've got like a little bit of you have to think about what you're going to do. There's a common misconception that we run into all the time. That is that you'll just turn on anomaly detection. It will detect anything weird. And that's kind of like the unknown problem. It's not really the way this works. What we're looking for is known unknowns. You have to know a little bit about what you're trying to detect in order for this to work. So you have some decisions to make. You have to know where your data is. You have to know what kind of data you're modeling. Are you doing metrics? Are you doing counts? Are you doing text, geopoints? Then you've got to know what kind of anomaly we're looking for. So you can see you've gone pretty far down this. We're not just looking for anything that's weird in the whole world. We're saying we're looking for spikes on Windows devices, right? We're looking for a high average packet count over a particular period. We're looking for a high level of firewall denies or a low level of log records. You have to sort of know what kind of anomalies you're looking for with a fair amount of specificity. And then once you've decided that, then you have your big decision. Do you want to do a population analysis across all, or do you want to partition it by the particular devices or groups of devices? And then, once that, if you're doing it, then in one way you're connecting to you're comparing against other entities, and the other way you're comparing against itself. So those are the decisions that you have to do to create an unsupervised machine learning job. It's a one-step process, which is kind of nice. So you create the data feed, which is the data that's going in there from the data view. You create your detector. These things, now once you've run the job, it runs continuously all the time. So it's always updating itself. And it takes you look back to build the model, but it keeps running. And that's a difference between the supervised machine learning. And then it generates an anomaly, and an anomaly is what we're after. And then, from that anomaly, we can generate alerts to go tell people something bad is happening. So here's what the results kind of look like really quick. And like I said, this isn't like in a how-to, but I wanted to show it. The model is indicated, and you have to look a little carefully at this. I tried to get the contrast up as much as I could. The model bounds, like it has created a line of what it expects, and that's what the gray area is. It expects with 95% probability that the record counts at this particular kind of day, if that's what we're modeling here, are between the shaded areas. So that's what your model is. That's your mathematical formula, is the shaded areas. I hope people can see those okay. Your actual results are the solid lines. So we could see this thing is producing results according to the model, which is what you'd like. And then right here in the middle, there's a red dot, which means there was a sudden drop. And that's way outside the model bounds. That's what's going to create an anomaly for you. So the mathematical model is the shaded part. That's where it's created by doing, lots and lots of regressions, I suspect, and some, PCA, common analysis. And that's how it created these shaded areas. The one other thing I'll bring your point to is that what falls out in the wash is, if you wanted to forecast the future, we've got a formula now. Like these model bounds this is a formula that can be expressed. So when we press the forecast button, it can move forward in time based on what it's seen in the past. And you could see like what it's going to look like in the future. And if it's trending up, like say like the log records are trending up, it will show that. So you can sort of see, like if we're modeling CPU usage or temperature, you could look in the future for a particular device and say, hey, it's not a problem now, but in 3 weeks, this thing's going to catch on fire. Maybe we should do something. So the model bounds is a confidence interval, and the red dot's an anomaly. And that forecast button is a great thing if you enable it. So let's talk a little bit. The last thing I want to talk about here is the anomaly scores. So the problem, right, is that anomalies, it's not trained data, and it's really easy to generate a lot of anomalies. And it's hard to tell which ones are real and which ones not, because the world's sort of an unpredictable place. And over time, the model will learn, and there'll be fewer anomalies because it's seen more. But nonetheless, this can be noisy, the anomaly scores. And this is not true just of Elastic, it's true of anything. And so the way that Elastic deals with this is it creates an anomaly score. And that's a number between 0 and 100. And that shows you how serious this anomaly is. And the way it calculates that is a very sophisticated algorithm, because this is the crux of it, right? You don't want a whole bunch of really bad-looking anomaly scores that turn out to, waste everybody's time. If you see an anomaly score of 98, you want to have some confidence that a human being needs to take a look at this and do something about it, possibly. So the anomaly score takes in 4 things. It takes in the probability of the result, but it also, just as important, it takes in how many observations were there, right? Like if I'm flipping a coin and I flip 2 heads in a row and then a tail, then the tail is going to be flagged as an anomaly because the model said, hey, I expect heads all the time. And so the tail is going to come up with like whoa, that is extremely anomalous if I only flip it 3 times. So the degrees of freedom, which is how many observations there are, goes into the anomaly score. So even if something is extremely anomalous, if we don't have a lot of observations for it, the anomaly score will get pushed way down, which is what you want. You don't want to be chasing stuff that doesn't have a lot of observations. If I flip a coin 1,000 times, a tail is not going to be anomalous. But if I just do it 3 times, it might well be. So the degrees of freedom and the probability of the result, which is shown here, there it is, probability, that's a negative, that's scientific notation. You know, it's very improbable, but that doesn't mean anything. What's really important is how many degrees of freedom there are. And that will go into the calculation of the anomaly score. And then there's a few other things that go in there too. The size of the confidence interval, right? We saw really tight model bounds before, but if the data is highly variable and then we see an anomalous result, that's going to drive that score down. The algorithm's going to knock it down because it's like, yeah, you know, we don't have a really good reliable model for this data, so we're not going to make people jump around if something weird happens. Then we're going to look at the adjacent buckets. And the last thing we're going to do is we're going to renormalize. So if I get the scores between 0 and 100, if I get a score of 98, but then the same device produces an even worse anomaly, like in 5 hours, I'm going to go back and knock this score down because it's going to be renormalized to between 0 and 100. So there's a lot that goes into this score. And the main point about it is that it's trying to save you time when you investigate them. We don't have a lot of control over how this score is calculated at this stage, but the formula is very sophisticated. It's an ensemble model, and you know it works pretty well to try and cut back on anomalies that aren't really that important. There's other ways to do it as well. So here are some other. These are just some other terms that go into here. The job rules is how sometimes, like there's an anomalous device that's always going to be anomalous because it's an oddball. We can create job rules to filter that device out so that it doesn't produce anomalies. Sometimes there's anomalies where it's really like you want 100,000 observations before you go chasing them. We can use job rules to deal with that. The rest of these are just terms. I'm sure there's, you know, we can read this at our leisure. One point I will make is that the results index is where these things go. So that's where the model lives. It's just an index, and you can read it and look at it and understand what it's actually saying. All right, let's take a breath and jump onto some supervised machine learning. So that's anomaly detection, generally done on time series data, etc. And so let's talk about supervised machine learning cases, because these are really just as interesting. Now, our use cases in observability and security are actually non-trivial here. But it's really used a lot in search. And I don't talk a lot about the search use case because, you know, like I said, I don't want to drone on here for like 5 hours. But these are the different types of sort of supervised machine learning. And that's, if we'll remember back, that's when we take a labeled set of data, either with a dependent variable of a number or a class. And we're going to model that, and we're going to create a model once. And then we're going to use inference to predict when new documents come in that'll tell us something about that. So the use cases are, say, for the use cases might be like the use case that I developed recently was in the security case. We're getting a whole bunch of alerts right over time, and the operations center, security operations center, is banging on these alerts all the time, and they're classifying them as false or true positive. Obviously, most of them are false positive, but once in a while they actually see some malicious activity and they have to go chase it. So the question is, a new alert comes in. I would really like to know if that alert, based on this classification, if I can classify that alert as likely true positive or likely false positive. And it turns out we can. And I wrote a classifier to classify the alerts. And then I have an inference pipeline, which we'll show in a moment, that takes the alerts, and a new alert comes in and it says, hey, this alert looks a lot like these other alerts that turned out to be a big problem. They have IP address that we've had trouble with in the past, a user we've had trouble with in the past, who knows what. And so you need to pay attention to this because this is likely a problem. Or this alert, 9 times out of 10 alerts that look like this are just false positives. So, back burner it for a minute. But you could also use it to say, like, is it an important customer? Like if we have customers classified as valuable customers based on their buying, we can create an inference engine to say if this is an important customer. We could do something, you could do something with airplane parts if you wanted. We could say the airplane parts The document might have 20 different or 50 different attributes on it. And if we have training data that says this part needed maintenance, we could accumulate enough data to create an inference engine so that when a new part came, when a telemetry for a part came in, it could flag it as, hey, based on what we know, this looks like it's going to be an issue, do something. Now, regression is where we're trying to model a continuous variable, and that's useful as well. Say if we suspect that packet loss is having a problem on signal quality, say we're doing phones, we can model that and we can sort of qualify how much packet loss has to do with signal quality. And we can even predict the signal quality based on the packet loss. But you could also, the use cases are tremendous for this, right? You could also say, how happy is this customer? If we have customers that say how happy they are on 1 to 10, and we know their buying patterns, we could run a regression and say, based on, even though this customer did not reply to our survey, we can make a pretty good guess that this is a happy or an unhappy customer. And then, of course, the outlier detection stuff is what I talked about earlier. How unusual is the size of a particular DNS payload? Like, how weird was that? Or how unusual are the access permissions for this user? So this is how, once again, it's the same thing. We're going to build a model, and we're going to apply new data to it. So you've got the same, the same sort of thing. You're going to choose your data. You're going to decide whether or not it's classed, really, whether or not you are looking to do a classifier or a regression. They're two flavors of the same thing. And then you need to choose your independent variables. There's a little bit of an art there, in the sense that if you're saying if your dependent variable is, say, the average packet loss, then you don't want to have the maximum packet loss as your independent variable, because those two things are obviously correlated, and that's not helping. What you want to try and do is look at other stuff that might affect packet loss, like CPU temperature or the firewall, or things like that. Overall network traffic, right? You want to take stuff that is correlated but not directly related to the dependent variable. And that way, you'll develop a regression formula, which you could use for inference, or you could just look at it and say, like, well, look at that. It is true that, this is the relationship between network volume across this segment and packet loss. And I could say that if my network volume goes up to here, then I can expect a packet loss here. And that's really valuable. So you can just use those numbers as they are, or you can create an ingest pipeline and populate them to something going in there. So here's the life cycle of a supervised machine job. You choose your dependent variable, you have your data feed, and then here we have to iterate, right? Because right now you're doing like your data science, and this is what we had to do with our pigeon data as well, right? You have to choose your features or independent variables. You have to run the job. You have to look at the results. You have to say, like, well, that's not exactly the correlation I was looking for. Maybe I need a different set of features. Maybe I need to tune some parameters. Maybe I need to look at slightly different data. Maybe I need to create a transform to aggregate data and then look at that. So this is an iterative process to create a successful one of these jobs. And, you have to go back and run it again. But fortunately, these things run pretty fast. I mean, you can iterate over, depending on the volume of data, you can run through this stuff really fast. And there's a lot you can do to make it faster if it is slow. So you're doing this manually. You're iterating through this to try and get the best formula possible. And once you have your model, now we can incorporate that result into pipelines or into dashboards. So this is how that's how it goes. That's how the life cycle goes. In terms of classification, right? This is pretty straightforward. You have this data, you got triangles and circles. This is from Elastic itself. What we do is we draw a line through the data, and we say everything above the line is likely a circle and everything below the line is likely a triangle. And that's all there is to it. It's the same thing we were doing back in 1979. You're always going to miss some, right? There's going to be outliers. There's going to be these weird, like, guys way out here that don't fit your model. That's just the problem with linear classification. So the question is, what happens if you have more than 2 dimensions, that, you know, you're not just trying to do a 2 variable regression, but a whole bunch of them, what we do is we have a plane, right? So if we have 3 dimensions, it's a plane. If we have 10 dimensions, I can't imagine stuff beyond 3 dimensions very easily, but really in some of this stuff, there could be 700 or 800 different dimensions. And all it is a plane in like 800 dimensional space, and everything above the plane and everything below the plane gets classified. But it's really no different than this. It's just more dimensions. So when we implement a classifier, if we want to, this is generally, once we've classified something, now once we have a good classifier that's accurate, then we want to use it on the new data coming in. So with my alert example, right, I've got a classifier, it's accurate, it's a good model. The question is, here comes some new data, now I want to use it. You throw it into an inference, you put this in an ingest pipeline. And this is an inference, you specify the model that you built, which, you know, the one that worked version, it took 24 iterations, but now I have a nice model. Yeah, I'm only interested in one class, the top class. Is it a true or false positive? I only have 2 classes I'm using. And then, you know, you can actually include some of the information as to how it arrived at its predicted severity. So this just goes in a pipeline like anything else. It's easy as can be. With regression, this is how we're going to predict. We're not going to predict a class. We're going to predict a number. So if I'm saying like that customer happiness number that I talked about, if I'm happy with my regression, if it's got a, you know, a good R square, like 0.98 or something, then I can put it into a pipeline, and when a new customer comes in, I can take a guess for you how happy he is on a scale of 1 to 100, or she is. And I'll also, if you like, I can include my reasoning behind that. What are the things that I used to determine whether or not they were happy? All righty. So there is how this stuff works together. So I would say, you know, in conclusion, despite all the buzzwords, it's all regression and line fitting. Here we see my pigeon is back in the, it's in the tree. It's funny. And, so are my buzzwords, but it's just the terminology really just reflects the different use cases. It doesn't, the different terminology, it doesn't really affect what we're doing here underneath the covers. And what's really, these are the same statistical techniques that have been around for a really long time. What's different, what's not old, is the really blazing fast speed of Elasticsearch, and with all the beautiful machine learning algorithms that they've implemented in a straightforward way. Between the two of them, we can do stuff like, stuff that would take me a month can get done in like, a 100th of a second back in the day. And that's what enables machine learning, is the processing speed of the data recovery and the speed of the algorithms that implement it. All righty. So down here I have just a few references. This is a great book by Ray Collier, who wrote a lot of the machine learning stuff. There's a second edition out. I don't know if a third's out yet, but this book is really helpful. It's 400 something pages, but it's a great book. Other than that, I've got some links on the presentation here, a little bit on, and one last one here on some pigeon research back in the day that I, was working with. Not quite that long ago, but so, and then the company itself, I'll just say for a minute, we are, we've been around since 2017. All we work on is Elastic all day long. We're a services partner, I think the biggest in America, resellers. We really like staff augmentation and migration. If you've got any kind of interesting use case, please send us an email, and that'll do it. I feel like 50 minutes. That's okay. I hope no one's fallen asleep.
No, that was very, very interesting. Thank you so much, George. That was really cool stuff. Yeah, absolutely. No, and it's so great to see somebody that is not paid by Elastic to have so much like happiness and pride of the product too.
Thanks. Stop sharing now, or?
Oh, sure. Yeah. I'll just take that off. Okay. So yeah, we have one interesting question, and I do believe that we have you to thank for this. I want to use Elastic for SOC, but I don't know how to set up, even though I have infrastructure for that. Please help me to solve it. Is there a course? Please guide me. So is there a way that they can contact you for further information, or do you have any resources that you would recommend?
Yeah, I think that if you read up on the security use case, let me see if I can get an intro to the. Like Elastic has three main use cases, right? Security, observability, and search. So let's see. Let me see if I can find a quick link for it. Oh, that's not what I want. There it is. So the SIM use case is what we want. So here's your starting point. Let me get back to my live stream. All right, so this is, all right, everyone in the studio can see that. So that's the starting point. But I would say generally, the decisions you have to make at the beginning, it's just like setting up any other SIM. It's really got the same capabilities as, say, Oxide. I mean, better capabilities really than Oxide or QRadar or stuff like that. So it wouldn't be different than setting up any other SIM. What you'd like to do is first decide whether or not you're going to run in the cloud or on-prem. So if you've got an infrastructure, it sounds like you'd be running on-prem. So if you're running on-prem, then the next thing you need to do is sort of size your cluster. And that's based on guesses about how much data you're going to have coming in. And to do that, you've got to figure out what your log sources are. Now for the SOC, right, you're going to get your Windows machines, your Unix machines, the authentication and security logs. You're going to get the firewalls at the very least, just to start with that. So you're going to figure out how much data those guys produce in terms of logs. And then, you would size the cluster. Then the next thing, before you start with any kind of content and developing content, you would want to really get your fleet agents together and start sending that data to your deployment. Now the data is coming in. Now, comes the fun part where we'll go in, and Elastic has like about 800 or so rules, detection rules. And then so many of which include machine learning jobs, like the kinds I've described, unsupervised largely. So you'll go through and you'll see for Windows, there might be maybe 50 rules. And you'll decide which ones you want to enable. Maybe you want to enable all of them. So you'll enable them, you'll customize them because every site's different. And then they'll start generating alerts. And then you'll assign those alerts to analysts and they'll attach them to cases in Elastic. That's one way to do it. Or they'll export them to a case management system and you'll just start running like any other SOC. So that's the 30-second version of how to set up a SIM. There's some nuance to it depending on how big and on where your log sources are. And once you've got the basic log sources in, there's all kinds of other stuff that you'd want to ingest as well, like threat intelligence. And there's all kinds of other interesting stuff we can do, like model users and stuff like that. But the basic thing is get the basic security sources ingested, which fortunately Elastic has these out-of-the-box integrations.
Awesome. Thank you so
much. Feel free to contact me if you want to talk more about it, of course.
And just a reminder, everybody, this will be recorded. This is being recorded, so this is in syndication. So we're getting a ton of valuable information from George right now. So you can check back later on when, compare with your notes. What does SOC stand for? Security Operations Center. So basically your security house. What would be your definition, George?
Well, it's not PC, but it's a large group of men in a dark room. Unfortunately, it's changing a little bit. It's where the Security Operations Center is a descendant of the Network Operations Center, and what it basically is a continuously running war room where alerts come in and people react to them. So these are the sorts of things that the larger companies have. The smaller companies generally, you can't dedicate a whole bunch of people to do that. So a lot of it is, but what you do have is a managed security provider for a lot of smaller firms, and they have a security operations center. So it's one room where all the alerts are coming in, all the anomalies that we just talked about are coming in, and at some point a human being has to take a look at them. And those are the human beings, are the analysts that work in the Security Operations Center, and then they'll decide whether or not it's a real serious problem. And if it is, then it will go to incident response, which is a different group.
This reminds me of the control room of all the 90s disaster films.
That's exactly what it is, yeah.
And I actually have a question. Since you are actually so close to working with clients, can you share any real-life examples where implementing anomaly detection with Elastic has significantly improved security or observability, or they've any like huge publicly shareable success stories that you can share with us?
Oh, sure. There's plenty of them. So the simplest ones involve detection of disruptions in log flow, right? So your firewalls are sending out logs, and if they stop sending logs, it means it's a problem. Your DNS servers are sending, they're processing requests all day long. If they start slowing down and they're producing way fewer requests at this particular time of day, then you need to get on top of that before the customers start calling up and screaming about them not being able to buy stuff on your website. In the security sense, like if there's if a device starts going haywire and starts sending out like all kinds of broken packets all over the place, it's probably infected and might be implementing a DDoS attack. It's important we've been in situations where, we've seen that, and it's like, wow, why is this happening? And why is it happening to this computer now? And it's all about advanced warning and fixing stuff before it really gets broke. That's the real value of this anomaly detection, because stuff doesn't really happen out of the blue so much as, it accumulates. So those are the sorts of things. I know that we just did a security use case, anomaly detection, that was really interesting with unusual websites that people are beaconing out to, both unusual in terms of other users seldom go to these sites and, in the organization, but also unusual in terms of the DNS name. The text of it is really unusual. And that's got a pretty high correlation with beaconing and infected machines. So, or also it's got a high correlation with clicking on bad links too. But at any event, you can get ahead of that and sort of say, like, why is this machine doing this? And, stop like an infiltration before it happens. And, so there are plenty of use cases. People are using it a lot. The trick is understanding that anomaly score and tuning out like any kind of noise, because you don't want to be chasing this stuff if it's not real. And then, carefully controlling your data feed so you're only getting the data that you want, and you're not getting anomalies for stuff that's not important. And then understanding the score. But it can produce some real nice results. You do have to iterate a bit. Because it is noisy at the beginning. And so, you have to adjust your job as you go down and try and make it produce but it also fixes itself over time too. So the number of anomalies, as the model grows, the number of anomalies usually goes down.
Gotcha. And speaking of like, noisy in the beginning, what are some common pitfalls to avoid or at least watch out for when starting with Elastic machine learning, especially for new users?
Well, let's think. Well, I think the biggest pitfall actually is not technical, but more communication. I think that it's a lot of times management will read anomaly detection and they'll make the assumption that this thing, you just turn it on and anything weird that happens, it'll let you know. And that's sort of the fault of, I don't know what I think it's the fault of just generally industry overhyping this stuff a little bit and saying, like, you just turn it on and it tells you anything weird that happens. And actually, as we saw, you have to, it can't help with the unknown problem. It can only help with sort of stuff that you actually want to model. So the biggest pitfall is explaining to management right away, look, it's not a matter of flipping a switch here. We need to think about which anomalies we want to model based on what we've seen here in the past, problems we've seen in the past, like, DNS servers blowing up, or people clicking on bad links or stuff. We're going to create anomaly detection jobs to detect this sort of stuff. But it's not just going to be like turning on a switch. So the biggest problem I see is that communication up to understand that, no, this is not just, not just a trivial thing to turn on, and it can't just intuit what you want. You have to be able to tell it a little bit of what you want. Now, I don't know if it's always going to be that way, but it certainly is the way it is now.
So it sounds like a little upward management of expectations as far as getting everything.
Yeah, exactly. Yeah, I think that's the biggest pitfall, actually.
Okay, well, that's a kind of a good thing. That's a soft skill that we can work on. And lastly, this is my last question. How are we able to follow or contact you? And where would we be able to get a copy of these slides to actually access all the reference links that you have?
Oh, well, would you want to, my emails, you can just contact me directly on the slides, of course.
Okay.
And do you want to throw my email into chat, or should I type it here, or what would you like?
Yeah, I can add it. What is it?
It's just, I can put it right here in the chat if that'll show up.
Sure.
So just contact me here. That's fine.
Okay, cool.
And I'd be happy to share the slides and also discuss use cases. And then, we've got, there's 20 something of us now, 20 of us now getting there. So, we'll get you to the right person if it's not me.
Awesome. Well, thank you very much. I really appreciate this talk, and you covered a lot of information that was very straightforward and simple to understand by the way you portrayed it, and that's very important. And again, sorry.
Oh no, I was just saying thank you for that.
Yeah, and again, everybody, if you want to, this is going to be recorded, so you can check it out again. Definitely scrub back to some previous sections where might got a little dense, or you just wanted to kind of jot down some notes for your own implementation. And thank you very much, everybody, for joining us. And we look forward to seeing you again. And thanks a lot, George.
Hey, thank you, guys. It was a real pleasure. Thanks for putting up with my personal journey here.
All righty. Take it easy.
See you later. Bye-bye.